Dr. Pavitra Bharadwaj and I am Associate Professor in the Department of Computer Science, Jesus and Mary College, University of Delhi. So friends, we have been talking about operating systems for the past few lectures, and today's topic is rather very interesting, and today we are going to talk about deadlocks. So what are deadlocks and how deadlocks are handled? What are the strategies to handle deadlocks in operating systems is all what we are going to discuss in today's lecture. So it's very interesting to know that when we were doing process synchronization, at that time also we had seen a situation where different processes, they will compete for the resources. And sometimes there is a possibility that a process wants a resource, but it is the resource is actually occupied by or is taken by another process, and therefore this particular process has to wait for the resource so that it can carry on with its execution. Now in this waiting, if this waiting goes on for an indefinite period of time, for a very large amount of time, for a very long period, then we say that the particular process is in a situation of a deadlock. Now if this same situation is applicable for multiple processes, then we say that all the processes are in a deadlock, right? So in a multi-programming environment, where we have seen that the resources are finite and the number of processes are very large, so in that case it is not always possible that whenever a process requests for a resource, it will get it, right? So therefore it has to enter a waiting state in that case, and sometimes this waiting state is prolonged, and therefore the requested resources are not available for the particular process. So this situation where a process is asking or is waiting for a resource which in turn is held by another process, and that process is also waiting for another resource, right? So this is like a chain or a cascading wait which is occurring, like process P0 is waiting for the resources which are held by process P1, and process P1 is in turn waiting for a resource which is held by process P2, for example. So in that case, such a situation or such a problem is known as a deadlock. Now why are deadlocks occurring? Why do deadlocks occur? Now it is more so because the way the trend is going on, the current computing trends, they have given birth to a large number of processes, because we are talking about multi-programming systems. So a very large number of processes are being executed at the same time. Then the programs are also multi-threaded programs. So each program can further give rise to multiple threads or multiple controls. Then further, the system also has a far more number of resources. Now resources, when we say, so we can understand that resources could be physical resources or those could be logical resources. So we will talk about the resources for which this competition or this race condition will be there. And also there is an emphasis on long lived file and database servers rather than batch systems. So now we no longer have batch systems, or only the background processes, they may run in the batch system, but most of the user processes, most of the foreground processes, they are active for a very long time within the they have to remain active on this particular domain. They cannot be deferred. So a large number of processes are executing, a large number of resources are there, and there is a constant demand for keeping the files and the database servers live for most period of time. So because of all these trends in computing, the problem of deadlocks is becoming more and more aggravated. Now when we study the deadlock, it is very important to understand the system model of a computer, that how the computer is actually, or how the operating system is actually working in the form of a system. When we say system, then we mean that a system is going to be composed of several components, and those components will work together in tandem for achievement of a particular task. Now, when we are talking about the system model with the purview of deadlocks, we are trying to say that a system will definitely have a number of resources, and these resources have to be distributed among a number of processes, and these processes, as we have already seen, that the resources are finite and the number of processes is very large. So, therefore, there is a competition between the processes to acquire the resources. So, what is done? The resources are partitioned or they are divided into several types or classes, and each type or each class, it consists of some number of identical instances. So, when I say instances, I mean that if a organization or if a computer, if it has got 2 CPUs, right. So, then CPU is the resource, and each of the CPUs which we are there is known as instance. So, instance means the number of units under the resource which are available. So, resources could be CPU cycles, resources could be files, it could be any input output device like printer, or it could be the tape, or it could be the disk drive. All these are examples of resources. So, so now when we talk about instances, so instance is very important, because later on we will see that how this sharing can be facilitated. When you have multiple instances, what is the effect? When you have a single instance, then what is the effect? So, if the process requests for an instance of a resource, then the allocation of any instance of the type should satisfy the request, right. So, if it does not satisfy, this means that the classification has not been done properly, right. For example, if a system say has 2 printers, and these 2 printers are located at 2 floors, say one printer is located at the 0 level and the other printer is located at the 9th level. Now, if a person sitting on the 9th floor wants to access the printer, right. So, then for that person, it should be that the printer on the 9th floor should be made available, the resource on the 9th floor should be made available. However, if we are putting both the printers, that is printer at the 0th level and printer at the 9th level are both under the same class, then the system may give any of the resources to the user. So, the printout can come on the 0th floor also and on the 9th floor also, which should not happen. So, in this case we have to understand that how the resources are classified, how the instances are created is also very important in order to make the best use of resources along with preventing the deadlocks. Now, there are other synchronization tools which we had discussed when we were doing the process synchronization. So, we had talked about the mutex locks and we had talked about semaphores, right. These are also considered as resources because, and these are a common source of deadlock. Both mutex and semaphores, they cause a large number of deadlocks. However, when a lock is typically associated with protecting a data structure, because this mutex and semaphore, these are created, these are like locks which are for particular data structure. So, a lock which is used to access a queue, and there will be another lock which will be used to access a linked list, right. So, each lock is actually having its own resource class, and therefore, definition of a class is not a problem even in synchronization tool, even in the logical resources. The mutex locks, the semaphores, these are logical resources of the system, unlike the physical resources we just saw, that is the input output devices or the physical memory of the computer. So, when a process is requesting a resource, right, before using it, so then the scheme is that first the process has to request the resource, then it will use it, and after it is used, then the resource has to be released back. So, a process is free to request as many resources as it requires to complete the designated task, but the number of resources requested, of course, obviously cannot exceed the total number of resources available in the system. For example, if the system has got only 3 printers, so no process can ask for more than 3 printers, but any process is free to ask for any number of printers up to 3. It can ask 1, 2 or 3 printers. Now, normal mode of operation of a process will utilize it in the same sequence only. That is, first the request is generated for the particular resource by the process. So, the process will request the resource. If the request cannot be granted immediately, then the requesting process will have to wait, and till the time it can acquire the resource, it will keep on being in the waiting state, right. Then the next is use. So, once the process which requested a resource, it gains the resource, it gets the resource, then it will operate on the resource, right. For example, if a process asked for a printer and it did not get a printer, then as soon as the printer becomes available for the process, the printing process will start on the printer. So, the task will be completed, and finally, when the task is completed, then the resource is released back to the system. So, the third step is the release step, when the process releases the particular resource. Now, there are multiple examples which we see of for request and release operation. Like, for example, when we say opening a file, we are requesting the file, and when we say closing the file, we are actually releasing the file. We have actually completed our task and we are releasing the releasing the file. Likewise, we have allocate and free for memory system calls. Whenever we want to allocate memory, the allocate system call is generated, and when the work is done, when the task is completed, the free memory system call is generated. In semaphores also we saw that there are 2 states. First state is called the wait state. So, whenever the request is wanted, whenever the semaphore is required, then a wait state is initiated, and once it is completed, the semaphore is available, then it goes into the signal. In mutex also we have the acquire state and the release state. So, the idea is that all resources, they have these 2 states, all the devices, they have these 2 states, that is the request state and the release state, and in between the request and the release, of course, lies the use state. Now, when a system, we are talking about a system which has got multiple resources and multiple processes which are asking for the resource, right. So, there you need a proper entry, or you need a proper database, or you need a proper inventory of which are the processes which are executing and which processes are waiting for which resources are available, right. So, for all this, the system actually maintains a table. So, for each use of kernel managed resources, or by a process or a thread, the operating system will have to check, right. First, it has to check and make sure that the process has requested and it has been allocated the resource that it has requested for. Now, a system table is something which will record whether the resource is free or allocated. So, for each resource that is allocated, the table will also record that to which process the resource has been allocated. So, whenever a process will request for a resource, then it is that is which is currently allocated to another process, then it can be added to a queue of processes which are waiting for this particular resource. So, basically this table is going to maintain a queue for every resource, and it is also going to keep a track of which process gets the resource at the moment, which process is holding the resource. It is very similar to the library. Like in the library, we have the books, certain books are very few in number. So, the users have to keep waiting. So whenever a user requires a particular book which is issued to another user, so the user will give a request to the librarian and there will be a queue for that book. So as soon as the book comes back, the person who is in the first in the queue will get the book. So likewise here also a queue of processes will be managed, will be maintained for each resource, and as soon as the resource is available, the processes are allocated this resource. Now when we say that when a deadlock will occur, that a set of processes is said to be in a deadlocked state when every process in the set is waiting for an event that can be caused only by another process in the set, right. So for example, there are multiple events. Now in this case mainly the event that we are waiting for is request acquisition, resource acquisition and resource release, right. So the resources could be physical resources like printers, tape drives, memory space, CPU cycles, or logical resources such as files, semaphores, mutex logs, right. Now for example, if there are 3 processes and each process and there are 3 CD drives, okay, CD read write maybe drive, RW drive, right. Now each process takes 1 CD RW drive, and then whenever a process will want the second CD RW, so then the process has to wait. Why it has to wait? Because there is no CD write available. So now what is the process waiting for? It is waiting for the event CD RW release to occur by any of the other 2 processes. So when those processes will release the CD RW, this process will get the second instance of the CD drive and it can proceed. Otherwise, till the time these 3 processes, each one is holding 1 CD drive and waiting for the next, there will be a deadlocked condition. Now in this case, all the 3 resources are of the same type, like we are talking about the 3 CD drives which are same. Now this could also occur in different types of resources. Like the example could be that we have a system which has 1 printer and 1 DVD drive, right. Now the process, there is a process, say PI process, which is holding the DVD, and process PJ which is holding the printer. Now PI requests the printer and PJ requests the DVD drive. So therefore a deadlock is occurring. Both PI and PJ actually need the DVD drive and the printer, but one resource, the DVD, is with one process, the printer is with the other process, and hence both are waiting for the second resource to be available. So this kind of a situation will lead to a deadlock situation. Now in deadlocks there are 4 conditions. How do we characterize a deadlock, right? So we say that whenever there is a deadlock, the processes, they will never finish execution, and all the resources which are held up by the processes, they remain tied up, and therefore other processes also cannot start. So therefore one deadlock, if it is occurring, then it can lead to multiple processes from being stalled from their execution, because more and more resources, they get held up by the processes, and therefore eventually there will be a condition when none of the processes can execute, and the system may require a manual restart, right. So a deadlock situation, how do we understand what are the conditions which will lead to a deadlock? So there are 4 main conditions that are very important to understand, and these conditions have to hold simultaneously in a system. That is, all 4 conditions must be true in a system at the same time to cause a deadlock. So the first condition that we see is the mutual exclusion condition. Now mutual exclusion means that the resource, at least one resource, is there in a non-shareable mode. That is, only one process at a time can use the resource. right? If another process requests that resource, then the requesting process is delayed until the resource has been released, right? So, mutual exclusion basically pertains to non-shareable resources. So, the resource can only be given to one process. If that process is holding the resource, all other processes will have to wait unless the resource is released by this. Then second very important condition is hold and wait. Hold and wait, the name itself suggests that the process is holding on to at least one resource and it is waiting to acquire additional resources which are actually being held by other processes. So, therefore, one process is keeping on with the resources that it has acquired, but it has not yet got all the resources, so it is waiting, and the resource for which this process is waiting are actually held by other processes. So, none of the processes can move ahead. Then the third condition is no preemption. Now, we have already discussed a lot about what is preemption in scheduling also. So, preemption means that the resource cannot be preempted, the resource cannot be taken back without the completion of the process or before the completion of the process. So, it will only be released voluntarily by the process which is holding it. And when will it release? Obviously, when the process has completed its task. So, when you have no preemption means that when a process acquires a resource, it will hold on to it till the time it is completing. In between, you cannot preempt the resource. And the fourth condition is circular wait. Circular wait basically means that if we have a set of n processes which are waiting, right, so that you number them P0, P1 and up to Pn, right. So, we have this set of n processes who are waiting and they must exist such that P0 is waiting for a resource which is held by P1 and P1 is waiting for a resource which is held by P2, right. Likewise, Pn minus 1 is waiting for a resource which is held by process Pn and Pn is waiting for a resource which is held by process P0, right. So, what is this? That each process is waiting for a resource which is held up by another process. So, for any deadlock to occur, all the four conditions must hold on and these should hold on simultaneously. That is very important, that for circular wait, hold and wait, mutual exclusion and no preemption. All these four conditions should be occurring at the same time for the resource to be or for the processes to enter the deadlock. Now, it is very important to see how we can pictorially or graphically how we can see that this deadlocks can be analyzed. So, how diagrammatically also we will see that how processes and resources can be shown and how we can detect whether there is a possibility of a deadlock or not. So, this portion we will be doing in the continuation lecture. Till then, thank you. Please keep watching CEC.